Also today is the day, 16T workshop. Let's say March 5th, March 6th, March 6th. I'm just flying on by. Okay, so for example, we might want to tell whether or not this series from k equals 1 to infinity of 1 over k cubed plus 2 converges or diverges. He's still using k's, right? Okay, I'll try my best. It's really, for some reason, super challenging for me. So if I was looking at something like this, I'm going to kind of, when I do examples in class, I'm going to try to go through them like I would normally approach any sort of series, meaning I would look at this and first think, okay, can I do the nth term test? And I can't, right? The nth term test doesn't help or fails because the limit of the, it's trouble. We call it the nth term test though, right? So I really want to use n because we call it the nth term test. I'm going to write the limit as n goes to infinity of 1 over n cubed plus 2 equals 0. Doesn't help us. And it's also technically not a p series, right? It's also not a p series because to be a p series, it specifically has to be just 1 over k to that power. Now, what you could argue to yourself, and you would be correct in doing so, is this looks very much like a p series, right? This is almost 1 over k to the third. The plus 2 doesn't really make a big difference on convergence or divergence. So if you can think to yourself, oh, well, 1 over k cubed, the sum of that converges, it's also pretty reasonable to think 1 over k cubed plus 2 also converges. And what we're going to do here is, although I would just, I mean, with practice, you can kind of be like, yeah, I know what converges, diverges. Here we're going to say, well, look at this. We can say that 1 over k cubed plus 2 is for sure always less than or equal to 1 over k cubed. And since that's true, we can conclude that the series for 1 over k cubed from k equals 1 to infinity, or sorry, 1 over k cubed plus 2, that series has to be less than or equal to the series from k equals 1 to infinity of 1 over k cubed, which we know converges. So the idea here is that if your series of non-negative terms is have terms that are all less than or equal to terms of another series that's convergent, that series is also convergent. Basically, you're saying this adds up to something that's finite, and this other stuff adds up to something that's less than that. So it's got to also be finite. I should point out the terms do have to be non-negative, because if you start introducing negative terms, then you can't really say anything about this. So basically, we're saying this sum here is less than or equal to this finite thing, and also greater than or equal to 0. So we can say, yeah, this series, the sum from k equals 1 to infinity of 1 over k cubed plus 2 converges. And typically we say what test we use, converges by direct comparison. And you can say with this other series. Or you can say by the direct comparison test. So that's kind of the very basic idea, is that if you can show that a series is less than or equal to some other convergent series, then it's convergent itself. And in a similar way, can I move the papers? Maybe, yeah, okay. In a similar way, we can say, for example, the sum from n equals 2 to infinity of n over n squared minus 1. I didn't start at 1 for obvious reasons. Oh, I see, can't help it. And I'll try to use k's, but n also works just fine. We can see that, well, if we look at n over n squared minus 1, it's certainly bigger than n over n squared. A lot of these comparisons or inequalities that we make up have a lot to do with just deciding, is your denominator bigger or smaller, right? This fraction has a larger denominator, so it's a smaller fraction. And then that's equal to 1 over n. And so that we can say, well, then the series for n equals 2 to infinity of n over n squared minus 1 is definitely going to be bigger than the series from n equals 2 to infinity of 1 over n. But that series diverges. as a P series. So since this thing adds up to infinity or gets infinitely large as we go further and further, this other series is also infinitely large. So we can say that the sum from n equals 2 to infinity of n over n squared minus 1 diverges by direct comparison, or diverges by the direct comparison test. You can also leave off the word direct. It's just that we often say it to contrast it from the limit comparison test, which is, in my opinion, the more useful test, but not always. So basically, that's the whole idea of the direct comparison test. If you're smaller than something that converges, you also converge. If you're bigger than something that diverges, then you also diverge. Yeah, and sure, yeah, that's that. So let's write it down. So here's the direct comparison test. But really, you should just remember the words I said, right? If something diverges and we're bigger than that, we also diverge. If something converges and we're smaller than that, we also converge. But here's the idea. It's written slightly differently in his notes, but it's fine. So if A sub k is less than or equal to C sub k for all k greater than or equal to 1, and the sum of C sub k converges. Oh, I should also say that these are positive or non-negative. Sorry about that. Your terms typically have to be non-negative. So if all these have something finite and these are all less than those, then we can say that the sum of A sub k also converges. And really, you can start wherever you want. We usually start at k equals 1, but right, we could start at k equals 5 or 10 or 1,000,000. Doesn't really matter. Similarly, if A sub k is bigger than or equal to B sub k, which is also always positive or non-negative, and the sum of B sub k diverges, then the sum of A sub k also diverges. A lot of times when they do this in like the actual definition, they'll just say one of them's A sub k, one of them's B sub k, and they'll say if A sub k diverges and B sub k is bigger, it also diverges, and they'll say if B sub k converges and is bigger than A sub k converges. But I feel like that's a little confusing, so I like to use like two different ones. So here we're saying if CK is the convergent one, then AK being smaller than it also converges. And if BK is the divergent one, AK being bigger than that means AK diverges. No big deal. So how to figure out what to compare with? That's kind of the question. So let's say we had, for example, the sum from n sure, fine, n equals 1 to infinity of the square root of n over n squared plus 5n plus 15. Usually, a good place to start is just by comparing the largest powers of n on the top and on the bottom. So we can certainly say that this series is less than the series from n equals 1 to infinity of the square root of n over n squared. I'm just looking at these highest power terms. And then I can rewrite that as the sum from n equals 1 to infinity of 1 over n to the 3 halves. And is this series convergent or divergent? Well, let me ask a different question actually before you give me the answer. If I'm saying that the thing I've got is less than some other thing, what's the only useful piece of information I could have here? Convergent, right? If this was divergent, knowing that this was less than that wouldn't help. Being less than something that's infinitely large means I could also be infinitely large, or I could be finite. So we need really for this to be useful, this to be convergent. And it is. This is convergent, right? It's a convergent P series. So then we can say that our series being less than that also converges. So this converges by comparison. Now, it gets a little bit harder if your fractions don't work out perfectly. we're not going to do this one just yet, but if, for example, if we were doing the sum from n equals 1 to infinity of the square root of n over n squared, shot myself in the foot there, that's fine. N squared minus 15, maybe we won't start at n equals 1, we'll start at n equals 10. This one still has the same sort of behavior, but you can't just do it by direct comparison, or at least not as easily, because I don't really know, right? I know that this is kind of like 1 over n to the 3 halves, but unfortunately it's bigger than 1 over n to the 3 halves because this denominator is smaller. So it's not super helpful to know that this is bigger than this, which is 1 over n to the 3 halves. Right? Being just like being smaller than something that's divergent isn't super helpful. Being larger than something that's convergent also isn't super helpful. So this one, we'll see in a minute, is better done with the limit comparison test. And honestly, that's usually my default go-to test if I have a series of a rational function where the top and the bottom are just power, or not even rational. You just have powers of k over powers of k, or powers of n, right? If you have something like that, even if they're not nice integer powers, usually the limit comparison test is where we're going to go. But we'll get there in a minute. And let's look at a couple more examples. So let's say we had the sum from n equals 5 to infinity of n squared over n cubed minus n plus 5. So when I look at that, what I really see, I see 1 over n. That's what I really see. Which I know is divergence. The series 1 over n. You do too. It's harmonic series, most famous divergent series you're going to see, right? It's the one that comes most often. So the hope here is that this thing, n squared over n cubed minus n plus 5, is that bigger than 1 over n? Well, if I'm not sure, what's that? Right, it's hard to tell. Here it is because we're starting at 5. If we cross multiply, you get n cubed bigger than n cubed minus n plus 5, and the n cubes cancel, and you can add the n over here. Say n is bigger than 5, and we're starting at n equal to 5, so that's fine. We're safe there. But right, it's hard to tell. Here we definitely could say that this series from n equals 5 to infinity of n squared over n cubed minus n plus 5, this definitely diverges by direct comparison. But right, exactly the point is it's not always easy to see exactly if this thing is bigger than something that's divergent or smaller than something that's convergent. Let me give you one more example like this before we do limit comparison. So let's say we had, maybe 2 more examples. The sum from k equals 1 to infinity of the inverse tangent of k over k squared. Inverse tangent. Have we talked about inverse tangent? I might be making an example that's not really good for this class. Okay, so this one, let's not do that one. Boo. I finally remembered to use k and it all went to hell. Obviously, it's the problem with k. I'm just kidding. What about in this one instead? The sum from k equals 1 to infinity of 1 over k times 3 to the k. Interesting. Well, if it weren't for the k, that series would be a geometric series that converges, right? So your ratio is 1/3. And it seems reasonable to say, well, I'm pretty sure that 1 over k times 3 to the k, that's less than 1 over 3 to the k. And maybe less than or equal to, right? Because technically if k was 1, they'd be the same. So here's my sequence terms, and they're smaller than sequence terms for a convergent series. So we can say, oh yeah, this definitely converges by direct comparison with the series, with the geometric series, the sum from k equals 1 to infinity of 1 over 3 to the k. So this one is also convergent, right? All the terms are less than. And I will say some people, I personally prefer to write it in a way where I'm saying that the terms of the sequence I don't know about are less than the terms of the other sequence I do know about. But some people like to write it as, some people would prefer to say instead that the sum from k equals 1 to infinity of 1 over k times 3 to the k is less than or equal to the sum from k equals 1 to infinity of 1 over 3 to the k. So people like to write it that way instead. Either way is kind of fine. You should probably just do it whichever way your teacher has done it in class, but both are pretty valid. I feel like this way is more the way it's usually stated in the theorem, as we talk about how just the terms have an inequality, and then we conclude that the series either converges or diverges. But you can also write it this way, and it's really not wrong. Okay. But back to the bigger issues that, right, sometimes you have things that are just terrible. Like, for example, the sum from k equals 1 to infinity of, where'd my example go? I lost it. It's fine. Sorry, brain. I was gonna start at 10. Something like n squared over. I'm sorry, my brain is not wanting to find the thing I wrote down before. Oh, no, that's totally, yeah. I'm sorry. Let's put this over here. All right, that's not the example I would do. I want to do this one. From k equals 10 to infinity of the square root of n over n squared minus 15.
You wrote k and then wrote n.
Motherfucker. Sorry. You guys are fine with ends, right? Okay. I'll just stop trying to do k. I just can't do it. It's clearly impossible for me to. I can do it like once or twice and then it's all goes down. So the issue here, as we said, is this is similar to the sum from n equals 10 to infinity of just 1 over n to the 3 halves, which is convergent. And I guess the bigger picture thing here is that when you're thinking about using either the comparison test or the limit comparison test, unlike other tests, you have to have an idea of what you think is going to happen. Meaning you have to look at this series and say to yourself, I think that converges. So I'm going to compare it to something that converges. Comparing this to something that's divergent is never going to work out. You're never going to get anything conclusive. But if you compare this to something that's convergent, you can usually get there. So specifically, if you're thinking about using either the direct comparison test or the limit comparison test, you have to know what you're comparing to. So I'm saying, okay, I think this converges. And I'm right, I know it converges. But what do I compare it to? Well, direct comparison's hard, right? This series, the square root of n over n squared minus 15, is bigger than 1 over n to the 3 halves. And that's not helpful. I don't want to be bigger than the thing that's convergent. I want to be less than the thing that's convergent. So instead, what we're going to do is we're going to use what's called the limit comparison test. So the limit comparison test says that instead of saying my thing is always less than something that converges, or my thing is always bigger than something that converges, what I can really do is just take the limit of the unknown sequence over the known sequence. And then if that limit is a number that is finite, then the series do the same things. So let me actually write down the test before we use it, because I think it's worth writing down. And I want to write down. I want to be precise. So here's limit comparison test, which we often abbreviate as the LCT. So let's say that the sum from n equals 1 to infinity b sub n is some series. And we want to know about the convergence or divergence of the sum from n equals 1 to infinity of a sub n. If the limit as n goes to infinity of a sub n over b sub n is equal to L, then these two series have the, oh, and I should say L is not, well, actually, no. Let's go this way. Then we can say the following. Two things. Basically, AN and BN do the same thing, but there's a couple corner cases we want to cover. So as long as L is a non-zero finite number, They either both converge or they both diverge. Because basically you're just saying, in fact, literally you're just kind of saying A sub n is L times B sub n. Essentially, right? Again, it's a little hand wavy, right? But that's really kind of the idea. You're saying eventually, as you go on and on and on, AN is L times BN. Close. So if these terms, if the BN terms add something that's convergent, and so do the AN terms, because they're just L times that. And the BN terms add something that's divergent, infinity, and so do the AN terms, because they're just L times that. The exceptions are if L is 0 or if L is infinity. Because if L is one of those two things, then things don't really add the right way. So here's what we're going to say. We're going to say if the series for BN converges, well, then so does the series for AN. As long as L isn't infinity. Or in other words, this limit can be 0 or a finite number if you want them both to converge. Similarly, if BN diverges, then so does the sum for AN, as long as that limit isn't 0. The reason being, what time is it? Okay. The reason being here, right? If BN is divergent, then all these terms are additive to infinity. But if AN is 0 times something that's just getting bigger, 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 we don't know if the terms for AN are getting bigger or not. Maybe they're really small, maybe they're really big. Similarly here, right? If BN is convergent, but AN is infinitely large times BN, then maybe AN is blowing up to infinity. So we don't actually know. Those are kind of inconclusive cases. So big picture, when I'm thinking about using the limit comparison test, I'm always going to use it when I have something that's n to a power over n to a power. Even if I could use direct comparison, unless it's like a super straightforward direct comparison, I'm going to use limit. Here's what I mean. So I want to know about this series from n equals 10 to infinity of the square root of n over n squared minus 15. And I'm going to do limit comparison with this series, which I know converges, right? I have to have the idea, oh, I think this converges. So let's do it. So the limit as n goes to infinity of, it's always the unknown series over the known series. So I don't know what this one's doing. I should say really the unknown sequence over the known sequence. But I do know what this bottom one's doing. And then when we flip and multiply, we get the limit as n goes to infinity of the square root of n over n squared minus 15 times n to the 3/2 over 1. And that becomes the limit as n goes to infinity of n squared over n squared minus 15, which is what? Right. This usually exploits that idea, but if you have a limit of something, oh my gosh, of a rational function where the power on top and the power on the bottom are the same, you get the limit that's the quotient of leading coefficients. Right, so here I'm just seeing, I'm getting 1 over 1. And since that's not 0 and not infinity, they both do the same thing. Specifically, it's not infinity here, right? It could have been 0, that would have been fine since we're looking for convergence. 0 is okay for convergence. But since this is definitely not infinity, then both series do the same thing. They both converge. So we can specifically say this series converges by limit comparison. Let's look at more examples. Let's say I wanted to look at the sum from n equals 2 to infinity of 2n over n to the 4th minus 1. Maybe I could figure out some direct comparison with 1 over n cubed or 2 over n cubed, whichever you prefer. But all I'm really doing is I'm saying I've got n to the 1st over n to the 4th, and I'm saying this is looking like the sum of 1 over n cubed. That is what I'm comparing it to. And I know that sum of 1 over n cubed converges, p series. So we're going to do limit comparison because it's easy. where the limit as n goes to infinity of the unknown sequence divided by the known sequence. What can this show me? This can show me convergence. It can't show me divergence because I've compared against something that's convergent. So you, again, I just want to stress, for these tests, you have to have an idea of what's going to happen. You have to be like, oh, I think this converges, so I'm comparing it to something that converges. So simplifying this, we get the limit as n goes to infinity of what? To flip and multiply 2n to the fourth over n to the fourth minus 1. And both of you should be able to tell me that limit is how many? Right. And 2 is not infinity, so they both converge. So the series we wanted to see from n equals 2 to infinity of 2n over n to the fourth minus 1 converges by limit comparison. Let's look at a couple more examples. So most of the time when I'm thinking about potentially using limit comparison test, it's really in these sort of examples where it's just powers of n over powers of n. You don't have anything really more complicated than that. Not that it can't be used for that, but it typically isn't. So let's see. Let's say we have the sum from n equals 1 to infinity of 3 times the square root of n over 4 n plus 1. So just like before, I'm just looking at the highest power of n on the top and the bottom. So this to me looks like the sum of the square root of n over n, which is the sum of 1 over n to the 1/2, which is a convergent or divergent series. Right, divergent. The divergent p series, our p is less than or equal to 1. So we are going to do a limit comparison with a divergent series. So we're only going to be able to show divergence. Totally fine. Typically, when you've done this enough times, you just start being like, well, instead of doing this divided by this, I'm going to do the unknown 3 root n over 4n plus 1. I'm just going to immediately multiply by the reciprocal of the known one. And then, as is typical with these, you almost always get the same degree on top and bottom if it's a rational or a powers of n over powers of n situation. So here I've got the limit as n goes to infinity of 3n over 4n plus 1, which is 3/4. And since it's not 0, they both diverge. Right? Infinity would have been fine here. 0 is a problem. And the reason you can kind of think about this, if you want to, is if you're looking at this limit, as n goes to infinity of 3 root n over 4n plus 1 over 1 over n to the 1/2, what you're basically saying is this ratio gets closer and closer to 3/4. So this top thing is always, or eventually, about 3/4 as big as this bottom thing. But since the bottom series diverges to infinity, 3/4 of infinity, still infinity. Whereas if this limit had been 0, then what you're kind of saying, oh, the bottom thing is getting infinitely large, but the top thing is like 0 times it. Or essentially this fraction is getting, if this limit were, which is not, right? This limit's not 0, but if this limit were 0, you'd be saying, well, the top thing is way, way smaller than the bottom thing. Maybe it's smaller enough that it's actually convergent. We don't know. That's why that would be inconclusive in that case. I feel like I have some examples here. Yeah, I do. So let's look at this fun example. The sum from k equals 1 to infinity. I'm trying to use k again. Of sine of 1 over k squared. Okay. So, oh, you know what I should have been doing this whole time? Nth term test. Just to check. But for each of these rational functions we've been looking at have always had powers on the bottom that were bigger, so they would have all had limits of the sequences that were 0. So none of these would have shown divergence by the nth term test. Here, again, if I were to use the nth term test, the limit as n goes to infinity of sine of 1 over n squared is 0. The sign is 0, which is 0. So no help. This one is actually kind of interesting. I'm going to compare it with 1 over k squared. So let's do limit comparison with, which means I'm thinking it's going to do what? Right, I'm comparing it to something that converges. Really, I'm just comparing against something that looks plausible, right? I didn't actually know it converges. I'm just trying something that I see. So if I do this, the limit as k goes to infinity of sine of 1 over k squared over 1 over k squared. This is actually kind of tricky. One way to do this would be to use L'Hopital's rule, which I know is not something everyone covered. The other way to see this limit, and again, this is kind of just it's a kind of tricky thing, is when you've got sine of something that's going to 0 over the same something that's going to 0, that limit is 1. Not super duper important. The problem is I'm pulling examples from the 21 series because that's where I have a more rich source of examples. So some of the examples I'm like, oh yeah, there's this thing, it might come up, I probably won't. So yeah, let's look at one more. I always say one more, and then one more, and then one more. Let's look at the sum from k equals 2 to infinity of 1 over the square root of k times the natural log of k. Oof. All right, and I really don't actually know what this is going to do. So typically, if I'm not sure if something converges or diverges, I start with my prime 2 examples. I'm always going to say, well, this is kind of my favorite example of a divergent series, the sum of 1 over n. Or I'm going to try this one, 1 over n squared. Right? If I don't have anything else to go on, these are the things I'm going to compare against to either test for divergence or convergence. So I usually jump to the limit comparison. So let's try that first. So limit comparison test. Let's test for divergence. Bless you. So we're going to do the limit as you can use k or n. I guess I'll try to use k. K goes to infinity of, again, it's the unknown over the known. So it's 1 over the square root of k times the natural log of k over 1 over k, which ends up being the limit as k goes to infinity of 1 over the square root of k times the natural log of k times k over 1, which ends up being the limit as k goes to infinity of the square root of k over the natural log of k. So this is another example where you could use L'Hopital's rule. L'Hopital's rule comes up kind of a lot in the limit comparison test, or it can. But here's another way to approach this one. Fact. The natural log of x is less than the pth root of x for p greater than or equal to 1. Eventually. Or in other words, the limit as x goes to infinity of the natural log of x over any root of x is eventually going to be 0. You can think about this graphically if you like. Here's what the natural log of x looks like. You know what? I could draw graphs all day long. It's more believable if Desmos draws them. And I do want you to see this just because it is worth knowing that, oh yeah, the natural log of x is really growing slower than any root of x. Let me show you, just because I think it's kind of neat to see. So yeah, paper's in the way. Go. So let's see, we've got y equal to natural log of x. Zoom out just a tiny bit. And then you can graph any root and it'll be bigger. So square root, not particularly exciting. Right, definitely bigger. Right, and definitely doesn't ever look like the logarithm can catch up, right? In fact, the logarithm grows way slower. But you could pick, I mean, we can do it the boring way, x to the 1/3. It looks like it's actually smaller, right? But then if you zoom out, it's eventually going to cross again. We saw it there for a second. So the logarithm might be bigger for a moment in time, but eventually any root of x is going to be the bigger thing. And I don't want to keep graphing it because we'd have to zoom way out to see it, but it is really true. Kind of neat. Yeah, it is kind of neat actually. So you can justify to yourself that this limit has to be what? Yeah, right. So this is going to be infinity, which then would show divergence. Does that show divergence? So what are we comparing it with? So this is where we compared it with this thing, right? Which is divergent. So here's another way of reading what we've done. We said the top thing is infinitely larger than the bottom thing. And since the bottom thing comes from something that's diverging, the top thing is infinitely larger than something that's divergent. So it is also divergent. So infinity is a-okay if you're showing divergence. So what we can say here is, yeah, this series from k equals 2 to infinity of 1 over the square root of k times natural log of k diverges by a limit comparison test. But it always feels kind of weird when you get infinity. You're like, infinity? Yeah, infinity is okay for divergence because you're saying, again, the top thing is infinitely larger than the bottom thing. Or, well, no, not or yet. Do I have another example here? No, we don't. Okay. Yeah. So what else do I want to say about the limit comparison test? Anything? I don't think so. Let me ask you both. Do you have questions or thoughts or I don't know, anything really about these, either the direct comparison or limit comparison tests? Okay, so I'm gonna say one more thing about them, then we'll kind of move on. The thing I said before is that typically you most often see them being used when you have just rational type functions. That is usually the prime usage of them. I'm trying to think of better words, but that's what you said. There are other examples like the one we just did, right? This is an example that's where it's not a rational function. You have a logarithm in there. So logarithms also can be examples of when you might use them. I did have one other example in mind, which is this one right here, the sum from k equals 1 to infinity of 1 over k times the natural log of k. And I do think this one is tricky. Like, I don't think you can show it converges or diverges by limit comparison. Because if you try and show it with, so if you try to compare it to the sum of 1 over k, which would be trying to show divergence, the limit as k goes to infinity of my unknown series over my known series, well, the k's are just going to cancel, and you get the limit as k goes to infinity of 1 over the natural log of k, but that's just 0, which doesn't help because we're saying, okay, this top thing is way, way smaller than this bottom thing, but the bottom thing sums to infinity. So being less than something that sums to infinity, you could also sum to infinity, you might not. If on the other hand, we compare it to 1 over k squared, well then, we have the limit as k goes to infinity of 1 over k natural log of k over 1 over k squared, which is really going to be the limit as k goes to infinity of k over the natural log of k. And just so you can see the way someone might do this a different way, you could certainly say k is bigger than the natural log of k. But if you wanted to use L'Hopital's rule, again, because we have what's called an infinity over infinity indeterminate type, if we use L'Hopital's rule and take the derivative of the top, you still need to write the limit as k goes to infinity. and the derivative of the bottom, which is 1 over k, then the limit as k goes to infinity of 1 over k, which is just k, is infinity. Which is also not helpful, right? Because here we were trying to show divergence, and 0 is the problem for divergence, right? Doesn't help. And here we were trying to show convergence because we were comparing something against something that converged. And again, this is no help. Because here we're saying the top thing is infinitely larger than the bottom thing. But if you're infinitely larger than something that's finite, yeah, that's, I guess you can say that way. You might still be finite, right? You might, I mean, infinite, that's, I don't love my words there. Like, I guess infinitely larger is not really the right word, but yeah, I don't know about that. Yeah, anyway, basically we're just, the terms are bigger on top. And so maybe they're too bigger, maybe they're not too bigger. We don't know. I would probably try, if this doesn't work, I would probably try one more thing before switching gears. I might compare it to 1 over k to the 3/2, kind of splitting the difference. And if I try that, which will still be shooting for convergence, right? Because that is a convergent series. If we do that, we have the limit as k goes to infinity of the unknown 1 over k times the natural log of k over the known, which then, if we simplify, becomes the limit as k goes to infinity of the square root of k over the natural log of k. And before we said that the square root of k is, any root of k is bigger than the natural log, which means this is going to go to infinity, which is still no help. So sometimes the limit comparison test just doesn't help, right? Some tests don't work for some types of series. This one, you could show converges using actually the integral test. Converges? No, sorry, diverges. This one diverges by the integral test. I'm trying to, but that's something we haven't talked about in class, right? I don't think we will talk. I'm trying to think, like, is there any other way to show this thing diverges? Maybe not. It definitely does diverge. Telling you it diverges and not showing you that doesn't feel super great. Can you use that other test? Sorry, I'm trying to think about if there's another way to do this. I don't know if there is. There's a test that keeps coming to mind, and now I'm forgetting what it is. Can't use the ratio test. Can't use that test. Where's the other test? Sorry, I lost it. There was something else I was thinking of, and now it's totally gone from my brain. Could we use direct comparison? Maybe. Yeah, maybe. So here's just something to keep in mind. The natural log of k is less than k. Right? Natural log graph does this, y equals x graph does that. And then if you flip them, 1 over the natural log of k is definitely bigger than 1 over k. Right? When you take the reciprocal of both sides of an inequality, change the order of the inequality. And then, nope, that's still not helpful. I know what I was going for, but that's not it. So yeah, this one might be out of our league without other tests. Okay, such is life. If he does talk about the integral test, let me know, but I don't think it's in the syllabus. Yeah. Right. Okay. It's a cool, I mean, we kind of talked about it a couple classes ago, I think, when I was showing you how you can take the areas under the curves, and that was kind of a thing, but yeah, it's not important. Okay, let me shoot you with one more example here, and then yeah, we can get to the ratio test. You see it? Maybe. So here's one more example. And if I try using the comparison test or the limit comparison test, it's not going to work out, I don't think. Let's see. If I compare it, it seems like 1 over k would be a good thing to compare it with, right? That seems plausible. A lot of times we're just guessing them. if we do this, the limit as k goes to infinity of the unknown over the known, oh, this is totally gonna work out. Right? We're gonna get the limit as k goes to infinity of k over the natural log of k. And what is that limit? Right, but which one's bigger? Is the top bigger or the bottom bigger? Right, k, so this limit is infinity. Again, I don't love this, but it's kind of what we're left with if we're trying to do it this way. If you wanted to, if you're allowed to, L'Hopital's rule does apply, and you take the derivative of the top and the derivative of the bottom, and then rewrite it as the limit as k goes to infinity of k, which is infinity. And since we were trying to show divergence, infinity is a-okay. Okay, enough of that. The big difference I would say between the limit comparison, direct comparison tests and the ratio test, which we use a lot, is that the ratio test, you don't have to have any idea if you think the thing converges or diverges. You're just comparing it to itself. And so I would encourage both of you to go back and watch the part of the last video I posted about where I talk about the ratio test. Because I do kind of talk about how the idea really is that what you're doing is you're saying, essentially the idea is that this series is going to be kind of geometric-esque. So in fact, let me grab, I do think you should go watch it, but let me grab this example here. So for example, yeah, in a minute, sure. So if I've got this series from n equals 1 to infinity of n squared over 3 to the n, it is not geometric. But if you go out for a long, long time, it starts to kind of behave in a geometric way. So if we write out terms, my first term is 1 over 3, and then my next term is 2 squared over 3 squared, and my next term is 3 squared over 3 cubed, and then 4 squared over 3 to the 4th, and so on and so on and so on. Not geometric, right? From here to here, you multiply by 2/3. From here to here, you multiply by something weird on top of it, right? It's not geometric. But if you go way, way out to like the 100th term, my 100th term is 100 squared over 2 to the 100th. My next term is 101 squared over 2 to the 101, and so on and so on and so on. And the thing is, from here to here, you're practically just multiplying by 1/2. Let me show you what I mean. If you take this term and divide it by that term, right, because that's how you figure out what the ratio is. If I take 101 squared divided by 2 to the 101 and divide it by the previous term. Oops. Gosh, got the numbers right, James, there. Sorry about that. Flipping and multiplying, I've got 101 squared over 2 to the 101 times 2 to, oh my gosh, I say 101 and I write 100. Oh, times 2 to the 100 over 100 squared. 2 to the 100 over 2 to the 101 gives me a 1/2. Right? All those 2's cancel out. And then you're left with 101 squared over 100 squared. And 101 over 100 is 1.01, and 1.01 squared is like 1.0201. So this is equal to 1/2 times 1.0201, which is pretty much 1/2. So the point is that as you move way, way out to the end, way, way out in this series, it doesn't have an end, right? The terms start to behave geometrically. And so if you can see that the limit of the ratio of the next term over the previous term is like a geometric ratio, then you can say that the series behaves in that way and converges if the ratio is less than 1 and diverges if the ratio is larger than 1. So what we can do is say, well, I'm going to look at the limit as n goes to infinity of the n+1 term over the n term. Technically, you're supposed to have an absolute value here, but most of these terms are all positive anyway, so it doesn't really matter. And if we look at that, the limit as n goes to infinity of n+1 squared over 3 to the n+1 And again, we do this often enough that we start just multiplying by the reciprocal instead of dividing by the thing. So instead of dividing by n squared over 3 to the n, we're going to multiply by 3 to the n over n squared. And then we combine the like terms, or group the like terms. We're going to write this as the limit as n goes to infinity of 3 to the n over 3 to the n plus 1 times n plus 1 squared over n squared. The 3 to the n over 3 to the n plus 1 becomes 1 over 3. And the n plus 1 squared over n squared is n plus 1 over n squared. And n plus 1 over n, using the little trick from 16a, right? That just goes to 1. And then 1 squared is still 1. So this becomes 1/3 times 1, which is 1/3. And then since that ratio, it's not really a ratio, but it's essentially the ratio. Since that ratio is less than 1, we get convergence. So here, you don't have to know that the series looks like something that converges or diverges. You're just going to say, well, I'm going to look and see what the ratio looks like. And if the ratio is a number that's less than 1, again, the ratio in quotes, because it's not really a ratio, but if the ratio is less than 1, you get convergence. If the ratio is larger than 1, you get divergence. And if the ratio is equal to 1, you got to do something else. It's inconclusive. So that's the main gist of the ratio test. You look at the limit of the next term over the previous term, and one of 3 things can happen. Bigger than 1 diverges, less than 1 converges, equal to 1, got to do something else. So next time we'll talk more about the ratio test. Let me know if he talks about the root test. I don't imagine he will, but I will tell you it's essentially the same as the ratio test. It's the same type of thing, taking a limit of a thing, and then if it's bigger than 1 diverges, if it's less than 1 converges. And then after that, I assume he will start talking about power series, Taylor series type stuff, which is kind of neat.